Okay, so we continue discussing transport in transport in okay, and what I said last time is okay. So basically, the system we are looking at is harmonic chain like that. With positions x1, p1, and masses m1, m2, m3, m4. And the temperature here is TL and the temperature here is T, right? Okay, and so the dissipation occurs only at the ends, right? Inside it's completely deterministic dynamics. And then we wrote the equations of motion. Okay, so let's just write it again. Okay, maybe I'll write it later. Okay, so then what I said is what today I'll show is that so we want to, the system reaches a steady state and we want to compute the current. And what I said is that you can show that you can write the current in the following form, T left minus T right. Okay, and this function is basically a phonon transmission. Okay, and so temperature occurs only here. Okay, there's no, this part is just depends on the system. There's no temperature here. Okay, that's the problem. Okay. So how do we derive this? And basically, it's first just good to recall what we did for the single particle case. So let's just say single particle connect to one bath. So the equations of motion are let's say x dot okay, and then okay, so I'll just so you can write it in various ways. This equation. So another useful way to write it is to notice that this is a linear equation, and you can write it as ddt of xp equals to 0. Okay, so maybe I'll put a minus m inverse and then k. And okay, so you can write it in this form, and this is like a matrix equation. So you can just call it some matrix A, U, and this is some vector of which is a let's say I just put a I'll just put some so this indicates a vector with components 0 and eta, right? Okay, so this is one other form I can write this equation, and then okay, so this equation, this maybe all of you know that you can write a solution which is basically EQT equals to e to the power minus AT. So this is like, so this part is, it's a linear equation and this is an inhomogeneous part, right? This is, so it's a linear inhomogeneous equation and the solution is given by the solution of the homogeneous part plus this part, and this you can in general write as okay. Okay, so this is a matrix and this vector. Okay, so this is in general you can always do this. Now the other thing we said is that I mean if you want to find steady state properties, there are two ways to do it. One is you can just write this equation in the following form. So if I use the fact that P is just mx double dot, then you can also write this equation equivalently in this form: mx double dot equals to minus kx minus gamma x dot plus eta, and then we take Fourier transforms, and this gives x minus m omega square x tilde plus k x tilde plus I gamma. So therefore, the solution in Fourier space is just right. So this you can write the solution in Fourier space like this, and then if you want steady state properties, we say that, for example, x square average is just given by right. Okay, and similarly x dot square average you can find this. Okay, and here we to compute this we have to use the fact that eta tilde omega. So we have to use the noise properties which are given as kpt by pi. Okay, so this was one way of solving it, and the other way to solve this equation was to write the Fokker-Planck corresponding to this equation, this set of equations. So the Fokker-Planck basically looks like del T of P equals to so minus. Okay, so maybe one can write a Fokker-Planck for this equation. So it's just linear equations, right? So you can write for U P is equal to so there's just a drift term del, and then there's a diffusion term which is dij. Right, so I mean, given a linear Fokker, a Langevin equation like that, the corresponding Fokker-Planck will have this form. This is okay? Or is one okay? So this is for a single particle, and then we saw that you can easily check that the equilibrium distribution is given by e to the power minus for a single particle e to the power beta. Okay, so now we go on to this system, and okay, so the first thing I said is that you can write some equations for correlation functions. Okay, so finally what we want to calculate is things like we want to compute things like pi square at different sites, and maybe something like qi ei plus 1, which gives the current. Right. So this sort of we basically want to compute all possible 2-point correlations. So I mean, instead of looking at the full distribution, maybe just looking at the 2-point correlations is enough. So it turns out that you can write. So if you consider all possible correlations, and basically this matrix, which is given by let's say qi qj. So when I say this Q basically includes both X and P. So this one I'll have some Xi Xj term, and then Xi Pj correlations. It's the same. So in general, this is the full set of correlations for the system, and it's for a harmonic system. It turns out that you can write a closed form equation for the time evolution of this. Okay, so. So let's write the equations of motion for the chain. So again, we can write basically qi dot and p equals to okay. So these are the and again I can write these equations in some matrix form. I define q equals to and then you can see that these equations can be written in the form dq by dt is equal to so this basically gives so there's a big zero here and m inverse minus sign. So I want to put a minus here, and then from so there's a part from here which I'll just call phi, and then there's a part which I'll call okay, so maybe okay, so these equations I can write in the form just this set of equations as d dt of is equal to, so this is just some force matrix, right? I mean, it's the dynamical matrix of the system. So I'll call that minus some phi of x1, x2, xn. Okay. So this phi basically will look like, so we'll just write it here. So phi will be some tridiagonal matrix in this case with elements k prime plus k, and then 0, 0, 0. And then 2k minus k 0, 0, 0, and then so on, right? So that's clear, I hope. So I mean, so this part will just give this thing. This is a dynamical equation, and then I have to add this part, and this I'll write as minus, let's say, some matrix which I call gamma L hat. Okay, so let me just say what this matrix. So these are matrices. Okay, whenever I put a hat, it means a matrix, and this is a vector. Okay, so you can guess what this matrix should be in order to get these equations of motion, right? So what do you think this matrix looks like? Diagonal and just one element is non-zero, right? So this matrix basically looks like gamma 1 and everything is 0. And gamma right looks like 0 everywhere, and just the bottom element is gamma n. Okay, so I'm just writing it in some matrix way because this will be really useful to get the results in some nice looking form, which also you can generalize to like arbitrary dimensions and so on. By n1. Huh? Sorry. Yeah. Oh right, yeah. So this element, right? Is made by n1. Okay, and this eta L and eta R are basically eta left is a vector with everything, this is eta 1 and everything else is 0, and eta R hat is a vector with everything 0, the last guy is eta n. Okay, so given this notation, you can see now that this is so this is just 5 times. Okay, so on the right hand, I'm going to have basically x1, x2, xn, and p1 to pn. Okay, and then I can put here. Okay, so this is slightly bad. Right. Okay. So now, so this eta hat basically is this plus this vector, which will look like. So these are the position. There's no a, and then eta 1 to 0 0, and then this last is eta n. Okay. And here, what should I write? I should basically have this gamma L and gamma R. Right? So minus. Okay, so this is fine, I guess. Okay, so it's exactly like this single particle case. Okay, so this whole thing, I'll call it this matrix A, and this is eta. So then formally I have this equation looks like dq by dt equals to minus aq plus eta. Okay, so this is some matrix A. Question? No. Okay, so now I can, so what I want to show is now that I want to construct the correlation matrix. So the correlation matrix is basically given by expectation of Q transpose, right? So Q is, where was Q? Q is this vector, and if I take transpose, then I basically get, where is the correlations? I get this correlation matrix, right? So basically I should take Q transpose and take expectation. Okay, now I want to write an equation for dc dt. Okay, so this will be basically, okay, I'll take expectation. So this will have two terms, Q dot Q transpose plus Q dot transpose. And this is equal to, so Q dot I use from here, so this gives and then Q dot transpose is basically minus Q transpose A transpose plus eta transpose. Okay, and now you can see that minus A Q transpose is basically C, so that's minus A hat C. From here I get minus Q transpose is again C, and then A transpose, and then have some extra terms. Okay, so plus okay, so now I will compute these objects. Okay, and the easiest way to compute this is to actually solve this equation. Okay, so from here we can see that the solution is basically given by Qt is equal to e to the power minus so if I take, let's say, Q eta transpose, so then I get Q eta transpose expectation, and both are at the same time, right? So so this gives me e to the power minus a t Q naught eta transpose expectation, and then from here plus okay, now we have to compute this. I mean, okay, so this object is 0, right? Because this is Q naught initial, this and noise, these are uncorrelated, and average noise is 0, so this is just 0. So we just need to compute this object, okay? So now what is this? Eta is just this object. So eta is basically 0, 0, 0 everywhere, and then eta 1, 0, 0, 0, and eta n, and then we, this is transpose, eta 1 and 0, 0, 0, 0, and then eta n. Okay, so if you multiply this and take expectation, clearly we will get something which is 0, 0, and then somewhere we get eta 1 correlation, and then everything 0, and then at the end eta n correlation, this is 0. Right, we get some matrix. So this is n cross n block 0, n cross n block 0, n cross n block 0, and this is n cross n block where everything is 0 except these two elements. Okay, so this is just coming from the bath. Okay, now this is of course, okay, these are two different times, t and t prime, because that's t prime and t. So this is at t prime, and this is at time t. So we are going to get a delta function, of course, and then we are going to get some factor which is 2 gamma kVt, right? KVt L here and 2 gamma kVt R here. Okay, so so this thing we'll just call it basically okay, this matrix, let's call it D. I mean, it's some matrix which has all these elements, or okay, maybe we'll call it D by 2. Okay, so okay, so this is this, and so there's a delta function. Okay, so some constant into delta t minus t prime. So we just so this constant part we take out. This basically involves t left and t right, right? And then you have this delta function. Okay, so then we just put it here, and since delta t minus t prime, you can you see that you get this only at t equal to t prime. So this becomes you just get the matrix D. Okay, so from here you basically get then this gives you D by 2. Okay, so this I okay, I think so. This is actually so this element is 2 gamma kb t left delta t minus t prime, and let me call the matrix which The D is defined as the elements are exactly this, okay. So I won't put a 2 here, okay. And actually you'll get a D by 2 here because this integral goes over half the delta function, right? So that's why you get a D by 2 here. So this is defined without the half factor. Okay, so this it just has 2 gamma KBTL. Okay, so we get d by 2 here. So this is this we just found is d by 2, and this is also, you can show it's as transpose, so it's the same matrix. It's also d by 2. Okay, so finally what you get is dc by dt equals to minus a c minus c a transpose and then plus D. Okay, so this is the matrix, this is the equation, and you can see that these are all the correlations and they form a closed set of equations. So this happens usually for harmonic systems. In other systems, if you try to write equations for 2-point correlations, they will be connected to 3-point correlations and so on, okay. But for this system, it just works out nicely, and you get these equations. And now in the steady state, what we'd say is that, okay, so in the non-equilibrium steady state, you set this to 0, and then you basically get an equation like AC plus CA transpose equals to D. Okay, so this is a linear equation, right, in C. So these are the unknowns, and A transpose, these are just some known matrices. They're just defined by this masses and dissipations that you put and the dynamical matrix. So this is completely known. This matrix is A. D is also known. It just depends on the temperatures at the 2 right ends. And so you can solve this somehow, right? So this kind of an equation is called a Lyapunov equation. I think Lyapunov equation. Okay, and so the way you should think of it is that if you just open it up, like just write all components, then all the elements of C you should think of as a vector. So let's say C11, C12, C13, then C21, C22. It's like a vector, and then you have some big matrix here, and this is equal to some vector here, right? And then these correlations are just given by inverse of this matrix times this. Okay, so that's how you'd solve. And in general, this is a very complicated set of equations. So this paper, Ryder, Lieb, Lebowitz, and Lieb, they actually solved this equation somehow. It's really a beautiful solution. But this you can do only when the masses are equal. Okay, so that's in general you can't solve it. And they found the correlation completely. And then I said you get this like flat temperature profile and the current which is independent of system size. Okay, so this is what I wanted to say, that you can write such an equation. And afterwards, we'll see that even for this other model that I said, where you take a harmonic chain, but then you add some stochastic process where things, momentums can exchange with each other. Okay, so then actually what happens is you have this, you still have these terms, and then you have some extra terms corresponding to this momentum exchanges, okay? But it still forms a closed set of equations, okay? So even though it's a non-integrable model and something which thermalizes and all, you can still, the 2-point correlations still form a closed set, and which is why you can get a lot of analytic results. Okay, so this afterwards we'll add some extra terms for this other system. Okay, so this is what I wanted to say about these equations and this the particular method used in this paper. And now we'll go to the second method, which is just solving these equations by Fourier transforms. Okay, so Fourier transforms, you should note, will only give the steady state. Yeah. So we can find the Gaussian. Yeah, I mean, because if you use this equation, of course, you have everything, right? And this equation has all information. Huh? When we wrote that, yeah. No, which derivative? C equal to QC. This one? Yeah. No, we didn't use any steady state. Right? But if P has time dependence, then there will be some derivative corresponding to P also. No, where is P? Oh, no, see, this is, I mean, see, I'm just using the Langevin equations. I don't use P. I mean, this is valid for any probability distribution you put. I mean, see, what I do is I just multiply this by Q transpose, right? Or the other way, maybe. I just multiply this by Q transpose, okay? And then I am imagining that I take an average over some probability distribution. So it's not like I take DDT of some expectation. I'm not doing, okay, so maybe you can just do it the other way. Just take derivatives and then take expectation. Yeah, that's what actually I'm doing, taking DDT and then expectation. Yeah, okay, so this will give transients also. And in fact, that's what afterwards what we'll see is that, see, this set of equations, it contains everything about temperature, like how does the temperature relax, right? I mean, so even if we ask a question about a system is in thermal equilibrium and you start from some temperature like that, this actually has all that information, okay? And we'll find that using this, you can actually write an equation for the temperature, how the temperature profile evolves, which is not the diffusion equation, but a modified kind of diffusion equation, okay? So that's what we'll do. Right. Okay, so now let's go back to the solving equations by Langeva, by Fourier transforms. Okay, what should I do? Swap this. Okay, the other thing maybe you guys can just try as a homework is, so this equation remains exactly same, right? Even for the n-particle system, it just looks like this. Okay, so now what you can do is, if you want to get this correlation equation, you can directly, okay, so you can just multiply this by, let's say, QK, QL, and do an integral over all Q. Okay, then you should be able to get back that the equations for the correlation functions. Okay, so even from the Fokker-Planck equation, you should be able to. So you have to do some partial integrations. So you have a QK, QL, and del del QI. So it looks like there are 3 Qs, right? But if you do some partial integrations, you'll find that it involves only 2-point correlations. Okay, so this is some exercise that you should do, and just verify that you get back this equation. Okay, so let me rub this. Ah. How did you conclude that okay, so okay, so even if it's non-Gaussian, you don't care, of course, right? Because you need the correlations to find the current and everything. So that, of course, is like if you have the correlations, you are in whatever you are interested in, you have. But why is it Gaussian? That also, okay, so the reason it's going to be Gaussian is that it's a, see, this is a linear set of equations, right? So when I wrote the solution, this is the solution. And okay, supposing you just put initial, so final steady state shouldn't depend on initial conditions, right? So I can put Q not equal to 0, let's say, right? So forget this term. Now, if you look at this equation, it's this eta is, I put in it as a Gaussian noise. Okay, so now this is like a sum of Gaussians, right? It's basically a sum of Gaussians. So therefore, Qt has to be a Gaussian at all times. Okay, and so in the steady state also it has to be a Gaussian distribution. Okay, and in fact, once you know C, then the steady state distribution is basically given by P Q is e to the power minus, so what is it? If you know the correlation, how do you write the steady Gaussian distribution if you know all correlation? C inverse, right? I think it's C inverse. Okay, and then there's some normalization. Okay, so that's the steady state distribution, which I mean, okay, so the important difference is that, I mean, if it was in equilibrium, this object is completely diagonal, right? The momentum part and there's a momentum part and there's a space part, and then these are completely uncorrelated. So there's no correlation between x and p. But now xp is correlated, which is why you have a current flowing in the system. Okay, so this is you know the full distribution and so on. Where is the one? Okay, so now let's rewrite the equations in just using x. So we have basically okay, maybe I'll just write it here. So m1. Okay, so these are the equations, and now I can write it again using this various matrices. As basically, it's clear that okay, I can write these equations as m x double dot equals to minus. Okay, so I think we already wrote it, right? So this is minus. Okay, so here x. Okay, so that's the force matrix, and this corresponds to this last springs being k prime, and all other springs being k. Okay, so I'm just putting the last spring constant different because we'll see that that has a sort of effect on things. Okay, so this is phi, and then we have this gamma L hat is basically gamma 1, and everything is 0, and similarly gamma. That is everything 0, and this is gamma n. Okay, so only one element non-zero, and eta l and are similarly vectors, right? So now again, if I just take Fourier transforms, what I get is so. Okay, x dot, so I omega. And I can bring everything this side, and then I can just write the solution, right? So x tilde omega is some Okay, so it has exactly the form as the one particle, except now there are two noises, and then G is some matrix now, right? Because all these are matrices, so this is some matrix, which is basically, so basically it's so you have to collect all these guys together. So it's minus M hat. Okay, so it's inverse of this matrix, right? Okay, so now we have the solution, and then we want to compute like the current, and we'll proceed in exactly the same way as, yeah. Okay, so here you can think of this like displacements around the equilibrium position, right? So then it's like basically zero there. Okay, so what's this thing? Okay, so we have the solution, and now what we want to find is, let's say, the current. That's the most interesting thing. And so I said earlier that you can calculate the current on anywhere, and it's most convenient to calculate the current at the end. Okay, so right from the reservoir into the system, let's say. So we saw this current expression is basically given by what was it? So velocity of the first particle into the force from the left reservoir, right? Expectation of that. Okay, so this is minus gamma V1 square, so, and we know how to compute things like this, right? And then there's V1 into eta 1, which we have to figure out. Okay, so now, okay, so how do we do this? I mean, so basically, what I'll do is I'll write it in a slightly more complicated way, and then it will things will. But the reason is that it will finally lead to a compact answer. Okay, and in sort of general form. Okay, so I'll write it in a slightly more, slightly different way. Okay, so first, if I look at this term, so it's V1 into, let's say, gamma V1. Okay, and this is first particle, right, gamma 1 V1. And this I can think of is like a dot product between this matrix right, this everyone agrees this is fine, right? I mean, if I take this into this, I'll just get some vector with gamma 1 V1 as the first element, everything 0. And then if I take, I'll get back this, right? So this is the same as this. Okay, so this is basically equals to, so this is what I call my vector, and this is transpose of the vector. So that's V transpose gamma, so this is gamma, what I called as gamma L hat, and then this is V. So this is V transpose gamma L at V. Okay, so this is what is this first term, and this I can also write as trace of Okay, so is everyone fine with this? This and this are the same. Okay, so anyway, this you can, if you just write down, you can see it's true. Okay, so so this I'll just write it then in this formal way. So this is equal to then there's a minus sign. And similarly, this one I can write as basically plus eta L into V transpose. Okay, so basically this eta1 V1 term I can write as okay, so maybe this is right. Yeah, it's right. So I can write it as V transpose into eta. So V transpose into eta, if I write, then that gives me V1 eta 1, eta L hat. So this is exactly equal to V1 eta 1, right? Because this is a column and this is a row, and this I just get the first element, and then I just rewrite it as trace of eta L into V transpose. So this is what I write. Okay, so now let's proceed. Okay, so now of course these are all at time t, and I just use the Fourier transform, and so I can write it as trace of. Okay, so let's just look at the first term. This term. So this is. And since this is velocity, so I'll get a I omega and I omega prime. So I'm just taking Fourier transform of these two objects. And then I have V tilde omega, V tilde, X. Omega prime and gamma L hat. This is just some constant matrix, right? And this is it. Okay, and I have to take expectation. Only a random variable is this, guys. So we just, and there's a transpose somewhere. This is transpose, okay. Okay, everyone fine? Okay, so now we put in our solution, which is that. And so we'll get. Okay, so this minus goes, and we just get omega, omega prime. And this is, so this is G times eta L. So G is a constant, so G plus omega, and then this is. Okay, yeah, I guess that's fine. And then gamma L hat. Okay, so now here we have to take these expectations, and we know that gamma L, this eta L transpose is equal to, right here. So it's basically gamma L hat KB TL and delta by pi, right? Okay, so if you just write the vectors and just look at the final matrix element, you'll see that this is correct, right? Okay, so and similarly, so eta L, eta R of course uncorrelated, and eta R is again same thing with gamma R and TR. Okay, so if we are almost done, okay, so okay, so now if we look at it, let's just okay, so now this term also we can do similarly, and okay, so out here if you again write this V as G times eta plus eta left plus eta right, and then take the correlation, it's clear that this term you'll get something which depends only on the left path, right? Right, because this involves eta left plus eta R. Right, and then when you take correlations, this is uncorrelated, and this will give you temperature of the left path, right? So this term definitely does not depend on T right. That's clear, right? Okay, so let's so only the dependence on the right temperature bath should come from here. Okay, so let's just write down the let's write the part of current that on T right. Okay, so we have this entire expression for the current, and we know this doesn't involve T right. So let's just look at the part from here that depends on T right. So that has to be this into this, right? And that will just give. So that is, so I'll just call it J right. And so that is now given by, okay, so if I put this factor of KB T right by pi, and then, so because of this delta omega plus omega prime, one of the integral goes, right, and we just get one integral d omega. And of course, this also goes. So which has to be true, we're in the steady state, right? So that has to vanish. And from omega prime is minus omega, so we get an omega square, and we get a minus sign here. And then we have trace of, there's a G plus omega, and from this eta R, we get a gamma R hat. And then there's this G plus, but now at minus omega, and the transpose, and then this there's gamma L hat. Right. So this is the expression. Okay, now this G matrix, if you look at it, so this object is basically just basically conjugate, like a transpose of this, right? It says the dagger of this object. So I'll just call it G minus omega. Okay, so that's the definition of G minus omega. You transpose and then take conjugate. Okay, so that's this object. Okay, so this is what we get. And now we ask what is the TL dependence. Okay, so clearly it has to be linearly dependent on TL, right? Does everyone agree? Yeah. TR, okay, so TR, I said, so you have to compute the eta R correlation. Eta correlation will be like the same thing, but it will be TR. So I'm just looking at the part from this which depends on TR, right? That's what I said. Let's just write the part which depends on TR. Okay, now, I mean, if I write the TL part, I mean, it's clear that it has to be, it will depend linearly on TL, right? Okay, so, I mean, if you think a little about it, it has to be the same thing, and except that the sign is TL, okay? Because you know that if TL is equal to TR, then it has to be 0, right? The current, there should be no current. So therefore, you see that okay, so I'll just write what are the, so current is okay, so in this system, the current is always linear, depends linearly on TL and TR, okay? So in fact, this you can see even from when we wrote this equation, AC plus C A transpose equal to D. I mean, this is a linear equation and this involves temperature, right? So when you write the solutions, all correlations will depend linearly on temperature, okay? So even the current has to be dependent, linearly dependent on TL and TR. And so it's clear that this current is linear in TL and TR, and it has to vanish when TL equals to TR. Okay, then it's clear that therefore the current has to be equal to KB okay, so let me just put a 4 here. Okay, so now, so this omega square, I just write it, I put a omega here and omega here, and then I call this gamma. Okay, so this gamma, so this new matrix I define is just okay, so we basically have this form which I wanted to derive, where this transmission coefficient is given by this object. So this is some given matrix, this is some given matrix, this is some matrix, and then you just have to take a product of this and then trace, right? And that will just give you some function of omega, and then you have to integrate over all frequencies. Okay, so this, I mean, it's easy to see that this is symmetric in omega. So I'll just rewrite it as 0 to infinity and put a 2 pi here. Okay, so that's the same thing. Okay, any questions? I hope, yeah.
How is it mentioned that like you have omega squared here, right?
Yeah.
So that trace of whatever is there, that should go like on the.
I mean, no, okay, yeah, see, this is omega square, but this has all this omega square sitting, right? This has omega 1 by omega square, this is not even larger than that, right? It's a big detail. So it's, this G had a 1 over omega square. Huh? No. Oh, sorry, I didn't write omega square. That's the A, right? I mean, even for the single particle, we had this minus omega. That's how we did the integral. Okay, so this object G plus omega, it's I mean, if you have studied condensed matter physics, it's just the Green's function of the for phonons. Okay, so I mean, so this is of the form 1 over. Okay, so normally, I mean, you define the Green's function without these factors. Okay, but here what I'm doing is I have this reservoirs, right? So effectively the Green's function changes, this is the effect of the reservoirs. Okay, so normally you just define Green's function like this with a plus minus epsilon or something with omega. But here I have reservoirs, so it just gets modified to this effective Green's function, okay. Okay, and if you write this Green's function in the time domain, it has a very simple physical interpretation. It's just like if you perturb it, if you give a small perturbation at, so this is a matrix, right? So if you look at the matrix elements and ask in time, ij, what does it physically mean? It just means like if I perturb at site j, what is the response at site I? Okay, so this again, if you just look at the equations and all, you can convince yourself that it's just this simple object. Okay. Okay, so now a few other comments that I want to make is this entire derivation you can also do for quantum systems. Okay, so if you are doing with quantum systems, first question is how do you write a equation for a heat bath, right? I mean, for here we wrote Langevin equations, it's easy. If you have a quantum system, how do you write heat bath? And there you can again write something like a quantum Langevin equation. And the way to get that is basically to first, it's difficult to just write equation which will have the correct, you want it to satisfy this fluctuation dissipation property, right? So that's difficult. So the way to do it is to actually have to model the heat bath in some way, okay? So in our case right now, we didn't model the heat bath at all. We just phenomenologically wrote the Langevin equation and it works fine, right? It takes the system to thermal equilibrium. So for quantum systems, so you need to model heat baths. And sort of popular model of heat baths is just to imagine is that, okay, so when let's say you have a single spring and you want to connect it to a heat bath. So the simplest and probably the only model that people use for a heat bath is to imagine that your bath is a collection of oscillators. Okay, so so there is some distribution of frequencies and then you couple all these oscillators to the particle. There's some couplings that you can put between each oscillator and this guy. And then you imagine that this is an infinite system, and initially you prepare it in equilibrium, okay, and then you connect this and then just look at its dynamics, okay. So then of course you expect physically that this should reach thermal equilibrium, and so it should be a good model for a bath, right? So it turns out that if you have a harmonic oscillator connected to a bath like this, then you can kind of derive effective equation of motion for this guy. And I'll just write you what is the equation of motion that you get. So you'd get an equation something like, okay, so now these are, if you have a quantum system, you think of X and P are the, let's say the, what is it called? Operators, right? Yeah. So these are the Heisenberg operators, right? So you're writing a Heisenberg equations of motions for these guys. And the equations you will write is like, I mean, you can just write these same equations. Okay, but now for the bath, what you find is that it's not, it's typically not like this delta correlated noise. You get some correlations in the noise. And similarly, the dissipation has a memory. Okay, so I mean, so one way to write this is, let's say, okay, so this is for a single bath. Okay, so instead of minus gamma V, I have some memory and then I write this. And the noise, what you can show is that the noise-noise correlation, it's easy to write it in Fourier space, not in real space. In Fourier space, this is basically given by See, I mean, normally you would expect a memory, right? I mean, not having a memory is a bit strange because, I mean, see, finally it's coming, you have a Brownian particle and the noise is coming from all these guys are hitting it, right? But then the same guy might be hitting it after some time, right? So clearly you should, normally you'll have memory. I mean, the noise, if the total force at one time should be related to the random force at later times, right? So normally you would expect memory, and not having memory is an approximation. But if you do a microscopic derivation, typically you'll find there's memory. Okay, so in the quantum case, the noise eta tilde omega okay, so let's see if this is right. Okay, so if you put high temperature, it should go to the classical result. So if you put high temperature, it goes to 1 over this, right? So that's cancels, and then you get gamma omega, and so in then it gives our classical thing. I think maybe there's no omega here. Okay, I think it's okay. Okay, so you have some noise like this, and so so the noise correlation is related to the imaginary part of this function. Okay, so that's the equivalent statement of fluctuation dissipation theorem. Okay, so you can write like this, and then again it's a linear equation in X. You can carry exactly this entire procedure, and the final answer pretty much looks like this. I mean, you get the same, exactly the same function, only this part changes. Okay, so I'll just write the quantum formula. Okay, so you just get something like this. Okay, so same transmission function, and then you have let's say the phonon distribution of the left path, and then the phonon distribution of the right path, and then each phonon carries an energy h cross omega. Right. So this is the final expression you get. If you take high temperature limit, you'll see that you get back this formula. Okay, so this I mean this whole thing is works both for classical and quantum, but this is only for this quadratic systems that this is works, right? Otherwise, it gets complicated. Okay, and okay, so this formula I should just also say that you can derive it. I derive it using this Langevin equation approach. You can also derive it in using various other approaches, and there are things called okay, so you can derive it like using something called Keldysh formalism. Then non-equilibrium Green's function is called NGF. And you can also do path integrals. This is like the Caldera-Leggett problem, right? Where you take oscillators and then do some path integrals. So you can also derive this formula using path integral approaches. Okay, but I would say that this is really the simplest approach, okay, and you can do it in one class, right? I mean, if you do any of this, it takes a lot of formalism, and finally you get exactly the same answer, okay, because the model is exactly the same. The baths are, I mean, you have baths which are modeled by a bunch of oscillators, and then you connect your system, and then you want to see what is the A, okay. And this formula is also sometimes called a Landauer formula. If you can do it for electrons, you'll get a similar formula. Where these are replaced by Fermi distributions and so on. Okay, so you can do it for phonons, electrons, photons, whatever you want, as long as they are non-interacting. Okay, so now 13 minutes. So we'll try to do some applications of this formula. Also, I should say this is, you can do it in any dimensions and in any, so it just, you just have to use, Green's function is still given by some mass matrix, force matrix, whatever force matrix you put, it's okay. And you have to see what points are connected to reservoirs, right? You can connect any number of points to reservoirs and put the appropriate dissipation matrix, and this will still work. Okay, so now let's apply this formula to get some, huh? Sigma is like the dissipation kernel. Okay, this will depend on the choice of your like frequencies you choose and how they're coupled. Okay, so I mean, if I have time, I'll talk of one popular model for this bath is called Rubin model. So that's just like a one-dimensional chain. So this bath itself is a infinite, semi-infinite one-dimensional chain, which is initially prepared in thermal equilibrium. Okay, so then you can and you couple one end to this system, and this you can explicitly solve and find what is sigma t. And yeah, maybe I'll state some results for that particular model. And but it depends basically on choice of the oscillator frequencies and how you couple them. Right, that's. Okay, so maybe this implies J average. So let's just stick to the classical thing. I mean, so one of the most important questions is the system size dependence, right? Now this actually we can see it, whether it's a quantum or classical system doesn't really make much difference, because it's basically these properties of the transmission coefficient which, and it's the same form both for classical and quantum systems. Okay, so we have this formula, and then we have this trace. Now this trace is, if you think about it, for this 1D chain, see, this matrix is just has one element non-zero, and this element has only one element non-zero. So if you take trace of this, basically what you'll get is, so if you want to connect this to this, this should be G1n, right? And this is also, if you want to connect this, it should be G1. So you just get one matrix element of this if you, once you take the trace. Okay. So basically what you get is, so now these are just numbers, and then G plus this is 0 to, okay, so G plus 1 and, okay, so you have this, so G is this matrix, right, so what you need is you have to take inverse and then take the 1n, this is the 1nth element, and then just mod square, right? So you have to find inverse of this this element particularly you need. So now what is the inverse of G1, what is that given by? So if I just want inverse of this matrix, this element, that's given by? Huh? Cofactor, right, yeah. So you have to find basically this cofactor divided by the determinant, right? Now, if you look at this, if you just stare at it, the cofactor, it just turns out to be k to the power n minus 1, okay? Because this is diagonal k and this is all 0, and there's something out here, okay? So the cofactor of this term is just a triangular matrix with everything 0 here and minus k is here, okay? And then you have something here. Okay, so if you do this, what you see immediately is that this G1n is basically oh, sorry. Sorry? Oh, right. Yeah. Yeah. So the dissipation comes only at the ends, and inside is just phi minus m omega square. Okay, so I can, so what is this matrix? So this delta 1n is determinant of this matrix. So let's say delta is, okay, so just rewrite this here. Okay, so let me just rewrite it. Okay, so I just defined this matrix Z as this object. So basically it's the same matrix, but I just scale everything by K, okay. And then so if you look at the first term, so the first term was K plus K prime minus M1 omega square minus K. And then I was dividing by K, so I divided the elements by, okay, or let's say I just want to rewrite it in this form so that it has the same form everywhere, okay. So I just rewrite it as 2K minus M1 omega square, and then I say minus, so I have to subtract this K minus K prime minus, and then so this is the same thing. This is just I'm writing the first element, and now I have to divide by K. So so this was so supposing I divide by K, then I get 2 minus M1 omega square by K, and whatever this object I just call it minus sigma prime. Okay, so sigma prime is 1 minus. Okay, so this, so therefore, after dividing this matrix by K, I just get something like this, right? So there's a minus sigma prime here, minus 1, this, minus 1, and so on. And the last element will similarly have some structure like this, right? Okay. And then this delta 1n is basically the determinant of this matrix, right? So if I took determinant of this matrix, when I took the cofactor, I got a k to the power n minus 1, and then I had to take determinant of this matrix. So I took out the k factor and put it in the determinant. So that's why I divided by this, and I just have one k left. Okay, I'm not sure k comes at the top or bottom. Can anyone quickly say where it should come? Okay, I mean, I think just from dimensional analysis, it should probably come at the bottom, right? Yeah, because this has 1 by k dimensions. I think it should be k inverse maybe. Okay, so so this is so I have to now find determinant of this matrix. That's delta 1n. Okay, so now I'll just, so there's a nice trick to find the determinant of this matrix. And basic idea is to, okay, so to use the fact that you can write this as delta 1n is equal to, okay, maybe I have to use my notes. Okay, maybe I should just say delta n. So this is just determinant of a matrix. Okay, it's not a matrix element. It's just determinant of this matrix. Okay, so this you can see, you can write it as 1. Okay, so I'll just make it's just some. I'll just take maybe 2-3 minutes. Okay, so what is this? I have to define this matrix D. So D is basically a matrix which is basically this matrix without the sigma prime. Okay, so the matrix D is basically you can just think of it as a A1 minus 1 0 0 0 minus 1 A2 minus 1 0 0 0 minus 1 A3 minus 1 0 0 and so on till AN minus 1, where K is equal to basically 2 minus MK by K. Okay, so this is, I mean, so this is just like, I mean, it's a kind of random matrix with tridiagonal random elements, because remember the masses are random, right? And the reason for doing this is I kind of separate the effect of the bath in this, so the effect of the reservoir is completely contained in this object, while this is just a property of the, I mean, of the system itself in some sense. Okay, so now this is, I mean, and what are these objects? So D1n is basically a determinant of this matrix. Okay, so D1n is basically determinant of this matrix. And D1n minus 1 is determinant of this matrix till the n minus 1 element. And D2n is the determinant of this matrix starting from this element to till the end. And D2n minus 1, you can guess, right, what the determinants of the matrix starting from A2 to AN minus 1. Okay, so this is not, I mean, you just have to sit and work, look at the structure, and you can see that this is true. Okay, so you start with taking determinant of this, and then just use the usual formula, this times cofactor of something minus this times cofactor of something, and then you have to somehow pull out this sigma prime parts, right? And then you have to do it from the other end, and then you just look at it and you see that it has this nice form. Okay, so, and then the final thing I want to say is that this matrix D itself, D1n, this actually you can write it as okay, so you can write it as basically, this is a 2 cross 2 matrix, and you can write it as a product of 2 cross 2 matrices, where each tk so I define these elements A, so A Okay, so this matrix you can write as product of 2 cross 2 matrices. So this is like product of random 2 cross 2 matrices. And then what will basically, there are lots of nice results on this, if you have such products of random matrices, I mean, how does it behave? How do the elements behave as a function of, so the only parameter here is, so all of this depend on frequency, right? Because this omega is there. And what we want to finally do is, we want to understand how this object depends on frequency dependence and size dependence, okay? And that we'll try to pull out by using results from this kind of theory, okay? Okay, but as a homework maybe that I'll give is, supposing all the masses are equal, right? Then it's easy to find this thing, right? How do you find this if all the masses are equal? Then it's just t to the power n, where t is just a matrix, right? Then you just diagonalize it and you can find t to the power n. And then you have to take this thing. So if you do this, you'll find this D1 for an ordered system. Okay, so this is just maybe homework. I mean, you can either do it this way, but you can also do it in like you just have an n cross n tridiagonal matrix like this. How do you find determinant, right? So there are various ways you can do this, and the answer is basically. So what is Q? So Q is basically is given by omega square equal to 2. Right, yeah. So this, I mean, so you have 2 minus m omega. So there's an omega here. So you write omega in terms of cosine. So this is actually, if you look at it, you recognize that this is the dispersion relation for the lattice, right? So given omega, you know what is Q, and you take this Q and put it in this formula, and that gives you the determinant of this matrix, okay? So you can either use this, it's just t to the power n, and then you can find what is this what is this particular element of this product, and you can find this, or try to find it in some other way, I mean, determinant of this matrix, okay? So for the ordered case, we know this, and then of course we can evaluate this explicitly, and then somehow we have to do the integral, but then it should be some simple integral, and then we should get back the answer. So we should see that it's independent of system size, and we should also get the precise value, right, that this Ryder-Lebowitz and Lieb got. So that's, so we are running a bit late, but hopefully first half of tomorrow we'll try to do both the ordered case, complete the ordered case, and also state the results for the disordered case. Okay, so I have a few copies of this. So these are some lecture notes on just this disordered harmonic chain that I have. So I have a few extra copies. I'll just leave it, and if anyone who is really interested in doing this can take that. Okay, so don't just take it because like a souvenir, but just if you really want to look at it, you can take this. So I have 2 copies. There are also other lectures on various things. Yeah, or I don't know if you can just read it and leave it back if you don't want, but you can just use this if you want. Okay, so I guess we meet after lunch. No questions, I guess. Right?